Hello, y'all. Welcome to lesson 70 of my DP chemistry curriculum. Today we're going over reactivity 1.2.3. This is an HL subject. We're going to be discussing standard enthalpy changes of combustion, delta HC, with the little standard, and formation, delta HF, with the standard. Data used in thermodynamic calculations, so we're going to figure out how to do that, and we'll deduce equations and solutions to problems involving these terms. All the data we need is given in the data booklet for combustion and formation. I believe those are sections 13 and 14 of your data booklet. So this comes from the idea that for every chemical process, we have changes in enthalpy in all reactions. Specifically, we are focusing on delta HC, and this would be the standard enthalpy of combustion, or standard enthalpy change of combustion. Oops. Change of combustion. These have units of kilojoules mole inverse. And then we also have delta HF, and this is the standard enthalpy change, of course, of formation. And once again, the units are still kilojoules mole inverse. This little theta right here, superscript, is what tells us that these are standard enthalpy changes, which we know from previous sections when we started talking about enthalpy. That means that we're dealing with 1 mole at standard conditions. So let's start off with combustion. So if we look at delta HC standard, which by the way is also sometimes referred to the molar enthalpy of combustion, the molar kind of gives it away that we're talking about 1 mole. So the direct definition is the energy change when 1 mole of substance is completely combusted in oxygen. Now, that can change based on whether or not this is a metal or hydrocarbon and what the products will be, but we're always combusting with oxygen, and this is going to be in standard conditions. All right. So one specific thing about this is that when we're dealing this, we just go straight to section 14 of data booklet because section 14 is where all the values are. You don't need to memorize any of them, and we're going to go over how to use them, but section 14 is your best friend when you're dealing with the enthalpy change of combustion. Now, the other one we're going to go over is delta HF formation, which also has the same naming condition. We can also call it the molar enthalpy of formation. This definition's a little bit trickier um, because this is the energy change associated with producing 1 mole of substance still, or forming, producing 1 mole of substance. But here's the caveat: from its constituent elements in standard forms. So because of this, sometimes we end up with weird equations. So an example might be delta HF of water, H2O in liquid form, which will be different from H2O in gaseous form, but the equation would be H2 gas plus 1/2 O2 gas reacts to form H2O. And we end up with these fraction coefficients because we need to keep it in its standard form, and oxygen starts off as a diatomic gas and hydrogen starts off as a diatomic gas. But we're only making 1 mole. So because we're only making 1 mole, we must have these weird coefficients. Um, One of the common other things that we run into with this is that what is a delta HF of an element? So like what if instead of making water, what is it of, for example, um, delta HF of oxygen? Well, for delta HF of oxygen, the standard form of oxygen is in fact oxygen. Therefore, there is no enthalpy of formation for elements. So elements in standard form do not have delta HF, or it equals 0 because they're already in their standard form. It takes no energy to convert them from standard form to exactly what they are. So where do we actually use delta HF and delta HC? Well, it turns out we go right back to Hess's law. And we're going to look at it with combustion first, and then we'll look at it with formation. So starting off with combustion, uh, we just find that delta H is going to be equal to the sum of delta H of combustion, of reactants, minus the sum of delta H of combustion of products. We already saw this in the last video when we did the energy cycle concerning the creation of methane, but we can do another example. Why don't we let's do another example, and we'll look at the formation of glucose, C6H12O6, and we will calculate with combustion. So we're actually going to find out the formation value, delta H formation, of glucose, but we will do it via our individual combustion calculations. So the equation for this is 6 carbon solid plus 6 hydrogen gas plus 3 oxygen gas, oops, O2, reacts to form glucose, C6H12O6, and that will be in solid form. Normally, we can just go ahead and look at CO2 plus H2O. Those are the products of combustion. And we saw this earlier where carbon combusts to form CO2, and that's our delta H1. Hydrogen combusts to form H2O, and that's our delta H2. Oxygen doesn't combust. Oxygen does not react with itself. And glucose combusts to make delta H3 because it makes CO2 and H2O. And so we know that delta H1 plus delta H2 minus delta H3, because we want the inverse reaction, gives us our delta H reaction. This is what we learned in Hess's law. But we can figure out what these values are through our section 14 combustion data. So we're going to take this a different route. We're doing the same route, but mathematically we're going to look at it just a little bit differently. So if we first look at the delta H combustion values, so delta H of combustion, we find that for carbon, it combusts with negative 394 kilojoules per mole. Hydrogen combusts with negative 286 kilojoules per mole. Oxygen, of course, does not react with itself. And glucose combusts with negative 2,803 kilojoules per mole. Then we're going to look at their coefficients because these are standard forms. And because of that, we have to multiply by the coefficients so we can get the actual values. So for carbon, we're going to multiply by 6. For hydrogen, we're going to multiply by 6. For oxygen, we're going to multiply by 3, and glucose 1. Now, we're going to get these total values, and that's just plugging this in their calculator. We get negative 2,364. We get negative 1,716. We get 0, and we get negative 2,803. Following our equation of Hess's law, the sum of the combustion values of reactants minus the sum of combustion values of products, we can see that all we have to do is just add up all these values and subtract this value. We can plug that into our calculator and find that the delta H of the reaction is equal to negative 1,277 kilojoules per mole. Now, the beauty of this is that we're still producing 1 mole of glucose, and we're doing it from the constituent elements in their standard form. So this delta H of reaction can also be written as the delta H of formation, and it's a standard value because we're only producing 1 mole of glucose. So we have just found delta HF via the usage of delta HC. So that's how we can apply Hess's law with combustion. Moving forward, we can also go with Hess's law, but with formation. It's a little funkier here. By the way, one thing I should say is this equation is in your data booklet. It's on the front page with all those things. The equation I'm about to give you right now will also be in your data booklet. The sum or the change in enthalpy of a reaction is also equal to the sum of the delta H of formation of products minus the sum of the delta H of formation of the reactants. You'll notice it is the opposite. So for combustion, we have reactants minus products. For formation, we have products minus reactions. Because we're looking at it from two different sides. Combustion is breaking things down while formation is building things up. It would be natural that they're inverse to each other if forming something releases energy while breaking something usually uses energy. To break bonds is endothermic, to form bonds is exothermic. So it makes sense that combusting, which is a process of breaking, and forming, the process of building, are inverse in how we calculate them. Basically, we're saying the enthalpies of forming products minus the enthalpies of forming reactants. Really quickly, why does this make sense? Well, products are what we are forming, so that's going to be our main value. We're subtracting the enthalpy of forming reactants, but really what we're doing, and here's the maybe brain twisty part, is we are adding the inverse of breaking reactants. Or adding the inverse of, yeah, so when we break reactants, we release energy, but we're trying to get that energy away from our original value. So this is why we subtract our reactants. That might be a little bit confusing. I'll leave it on the chopping block. You can just use the equation given in the data booklet. Anyways, let's take a look at the enthalpy of formation using, of course, combustion. So the inverse of what we did before. One final note is we still must consider coefficients. We have to consider them because these are standard values. So our values we get are only from 1 mole. So let's do an example with propane. So C3H8, propane is a gas. If you watch a lot of King of the Hill, you probably see propane and propane accessories. But when we combust propane, we react it with oxygen to, of course, get carbon dioxide. We'll get 3 of those, and water, H2O, and we'll get 4 of those. So we'll do exactly what we did before, but this time we're going to look at delta H of formation values. So for propane, this is negative 105 kilojoules per mole. For oxygen, it's in its elemental state already, so it has no value. Carbon dioxide, when we form that, that is negative 394 kilojoules per mole. And water is negative 286 kilojoules per mole. If we go ahead and look back up, you'll notice some parallels. Carbon to turn into CO2 via combustion is negative 394. Therefore, the formation of carbon dioxide, so if we go here, to burn produces 394. To form CO2 also produces 394. So this just makes sense because they are the same reaction. The combustion of carbon is the same thing as the formation of carbon dioxide. Meanwhile, water, which we saw in a previous equation from last video, is still negative 286. So moving forward, our coefficients, we must consider that. That is 1 times 5 times 3 and times 4. So our total is going to still be negative 105. 0 times 5 is still 0. 394 times 3 is negative 1182. And negative 286 times 4 is negative 1144. We still have to plug it into our equation. Delta HF is going to be equal to the sum of the delta HF products. Oops, sorry, and I made a mistake. We're looking at combustion. Delta HF products minus the sum of the delta HF reactants. So we'll plug these in. Negative 1144 plus a negative 1182 minus a negative 105. The minus and negative will cancel out, and we will get a total of negative 2221 kilojoules mole inverse. What you need to be able to do here is just be able to use the equations in your data booklet and recognize when you're using each one. In this case, the combustion reaction is the reaction, so delta H of reaction is the same as delta H of combustion. And we know it's combustion, or we know we're using formation values because we explained that we were, but you could easily use combustion values as this is a combustion reaction. Anyways, I hope this helps you a little bit. What I suggest you do with these problems is practice, practice, practice. The one thing I see students do with enthalpy problems is they use the wrong equation, because now we have learned 3 equations that I will just quickly review. If you're using bond enthalpy, it's bonds broken minus bonds formed, which is another way of the bonds of the reactants minus bonds of the products. If you're using combustion, it's going to be reactants minus products. But if you're using formation, it's going to be products minus reactants. While these may seem confusing to memorize, you still can, of course, but also you can just think about what you expect energy to be. We expect that we're going to release energy in forming bonds. Well, we're going to use energy in breaking bonds. Combustion, we are going to very likely always release energy. Formation usually takes energy, and it can vary from product to product. Sometimes we can also release. My suggestion is look at what you're doing. Oops. Look at what you're doing and look to see if any of these match. One of the number one things is DP exam will just tell you, use bond enthalpy. This is a combustion reaction. This is not a combustion reaction or bond enthalpy, therefore it's got to be formation. So DP will usually be either pretty clear in the first two or completely ambiguous, in which case you use the last one. I hope this little piece of advice helps, and have a great day.